So, when we ran out of time on Monday, we were in the process of figuring out what VL of T was for our example problem. Don't know about you guys, but I cannot remember crap for Monday, so we might have to scroll back through and look at some things. So we were solving for VL, and effectively we needed L times omega D times B4. So let's figure out what that is real quick. I don't even remember what L is. So L was 10 henries. Omega D was, let me put this in as an exact number just for the sake of argument. 100 squared minus 93.75 squared. And then we multiply that by B4. Sorry, this is taking forever to scroll. Square root of 100 squared minus 93.75 squared. So that is x. Okay. So 10 times x times 45 over 8 divided by 10x. I think that's just going to be 45 over 8. Times x times 45 over 8. Divided by 5.625 volts is what I just got, which is 45 over 8. Yep. So let's write that bit. So we're going to have 45 over 8 cosine 34.799 T. And now we need L times alpha times B4. So that's 10 times 93.75 times 35 over 8 divided by 10x. 15.154 sine 34.799 T. Close that all off e to the negative alpha T, where alpha, excuse me, is the 93.75 T. So we have VL and we have VC. And now we're going to add these quantities together, because just to recap things here, our goal was to figure out what this resistor current is. So we're saying the voltage drop across the resistor is just the sum of the voltage drop across the capacitor plus the voltage drop across the inductor, and then divide that by the resistor value. So look at what VR of T is going to be. So that's just VL plus VC. So we see up here that VC has a term of negative 45 over 8 cosine 34.799, and VL has positive 45 over 8 cosine 34.799. So those guys are going to cancel each other out, obviously. So we're not going to have a cosine portion to that at all. For our sine bit, we have negative 15.154. And we have another negative 15.154. So I'm just going to take that by 2. So this is going to look like negative 30.308 sine 34.799t e to the negative 93.75t. And now I need to add any DC terms I have, so that's going to look like a plus 45/8 over there. And we divide this by our resistor value. Scroll up really quickly and see what resistor we were looking at. I think it's the 3 kilo ohm. Yes. So divide by 3,000. So we get negative 10.103 sine 34.799t e to the minus 93.75t, and then 45/8. 20,000 plus 2 milliamps should be our resistor current. So let's throw this into LC Spice and just make sure things are behaving the way that we expect them to. Always a good idea, especially when these guys get as complicated as this one in particular was. Yes.
Why do you add the 25/8 volts and then VRT inflation?
So, great question. If we look at VC over here, it has a DC term of 45/8. And so VC plus VL, well, VL didn't have a DC term. So that's why we just have the 45/8 and nothing else. Yep. Good question though. LT Spice here in the middle. At some point I will have to clean up that desktop, but today is not that day. This year is probably not that day. So sorry, my memory is crap right now, so I don't even fully recall what the circuit looks like. So during the transient condition, all right, so we're gonna have a 3 milliamp source up. I don't want to label a network. I want to add a component. I think I just hit the wrong button. And then just effectively drawing things out, and I'll drop the components where they need to be here in just a second. So if memory serves me correctly, this is my 3 kilo ohm resistor. And this other one is a 5. And then over here on the right-hand side, I have my 10 Henry inductor. And then across here, I have a capacitor whose value is 10 micro. I'm going to put the ground node on the negative polarity terminal of my capacitor, which seems like it's going to be an odd place up here on the top right, but it'll all be okay. I'm going to label the positive polarity node VC here. And now I need to put my initial conditions. So the initial condition on my capacitor voltage, let me scroll down and find that really quickly, was 0 volts, and the initial condition on my inductor current was 0 amps. Okay. U, just the letter U. It'll take care of the rest for you. Yep. The only thing for those like engineering symbols that you really have to worry about, if you just put in an M, it's going to treat that as milli, regardless of whether you put it in as a capital M or a lowercase m, because it does not care about capital letters or whatever. So if you want to do mega anything, you have to literally type in MEG for it to know you mean 10 to the 6th. That's the only one that I found where it's weird. So IL1 equal to 0. And then I'm just going to make up a number here and we'll change this if we need to. Let's run this for 100 milliseconds or 0.1 seconds and just see what shakes out. And if we need to change it because things haven't settled, we can. So run our simulation. The first thing I'm going to do is add a second plot plane. So in the top one, I want my, was it our capacitor voltage we found first? Was that one of the quantities of interest? Let me look up here. And then the other one was the resistor current. Okay. So for our capacitor voltage, that would just be this guy right here. Looks like it settles. So that's fine. And then here we want this resistor current. That also looks like it settles within 100 milliseconds. Looks like I could have shortened the simulation time to somewhere in the ballpark of 75 milliseconds or so, but that's okay. All right, and so now we're going to put in our mathematical expressions. So for VC, we had, let's see, negative 45 over 8. It's not going to like that, so I'm going to put it as negative 5.625 times the cosine of, and this is going to have an error in it kind of intentionally. I'm just going to type in exactly what we put in. It's going to give me the wrong graph and we're going to fix it. 34.799 times time minus 15.154 times sine of 34.799 times time, close double parentheses there, times exp negative 93.75 times time plus 5.625. So it settles to the same thing, but it looks significantly different, okay? So the reason why it looks so different is because LT Spice does everything with linear frequency, not angular frequency. So we need to correct that 34.799. Instead of being in radians per second, we effectively need it to be in degrees per second in order for things to work out. So I'm just going to right click on that and I'm going to add in a little conversion factor. And that conversion factor is just 180 over pi. And I get pi by literally typing pi. And I need to do it everywhere I have an omega d. And now everything perfectly matches, right? My scale on the left-hand side is exactly equal to the scale on the right-hand side. The red curve completely overlapped the green curve. So our solution for VC of t, absolutely correct. Now let's check our work on our resistor current. So I'm going to add a trace. So if I remember correctly, this was negative 30.308 times sine 34.799, yeah, times 180 over pi times time times exp negative 93.75. Sorry, that is wildly wrong because that's the voltage and we want the current. That current was 10.102 milliamps. So 0.010103. Sorry about that. Plus, I think it was 2 milliamps. So 0.02. And so this looks a little different, like very, very similar. But notice that the scale on the left-hand side and the scale on the right-hand side of the page are not the same. So I'm going to right click over here and I'm just going to change this. So the top is 2, the bottom is half a milliamp. So I'm just going to do the exact same thing over here. Make the top 2 and the bottom half. And it's still off by some small amount. 10.103. Let me double check here. So looks like the problem is with the DC offset. So 5.625 divided by 3,000 definitely does not come out to be exactly 2 milliamps. That was just rounding error on my part. So this should be 1.875 milliamp. And let's see if that fixes that. There we go. I just didn't have enough significant figures on my calculator shown. I apologize for that. 1.875 milliamp. Okay. So we finished that example problem. And so now my goal was to just either work more examples or answer your questions. So which way do you guys want to play it?
Questions.
Okay, which homework question or questions do you want to look at? I'm venturing a guess you guys probably want to look at the one with the dependent sources. Yeah. Yep, that always seems to throw you guys a curveball, even though it's literally nothing you haven't done before. It's just in a slightly different form. All right, so let's take a look at the problem containing a dependent source. I don't remember exactly what that is off the top of my head, so give me a moment to pull it up. Excuse my damn mouse. So the parallel RLC circuit one or the series RLC circuit one? Oops. Okay, well, let me go back. Apparently I changed the stuff on Google Drive and not here. I just should be the same. So So this guy right here. Okay. All right, so give me just a moment to draw this out. So I've got a 9-volt source and then a switch that's opening. Oh, that's the wrong thing. 2 ohm resistor. Through which some current IA of T is flowing. Then I have here a dependent source. That is positive polarity on the left, negative on the right. 3 IA of T. 7 ohm, 25 millifarads. 4.444. I'm gonna work this as if that 4.444 ohm impedance were, or excuse me, the inductance. Well, let's see. So that's 4/9. Yeah. I just can't do fractions on the program that I use to do this, which is why I had to do it as 4.444. It'll all work out in the wash since it's just a tiny amount of rounding error. Let's see here. So here is, oh, and I don't know why I drew that capacitor as if it were a resistor. IC, IL, and V. All right, so first thing we're gonna do is exactly what the problem tells us to do. We're gonna analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our switch is closed and we are at DC steady state. So our circuit should look something like this. So here is our 9-volt source. We have our closed switch. Here we have a 2 ohm resistor. This is IA at 0 minus, which we are going to completely not worry about, I think. Unless we were explicitly told to pay attention to it, but I don't think that we were. So this is what our circuit looks like at t is equal to 0 minus. So what can we glean from this without doing any real circuit analysis whatsoever? So I think that we can see very easily that V at 0 minus is simply 0 volts. Because our short circuit representing our inductor is in parallel with the open circuit representing the capacitor, and the voltage drop across a short circuit is always 0. So we know that that one is 0 right off the jump. Okay. We can, Yep, IC is also 0. Because that is the current flowing through an open circuit. So the only thing that we have to really think about per se is IL at 0 minus. So a couple of different ways that we could solve for that. Me just looking at this thing, I feel inclined to do Kirchhoff's voltage law around the outside, meaning that I would have -9 volts plus 3IA at 0 minus plus 7 ohms times IL at 0 minus is equal to 0. That's just Kirchhoff's voltage law around the perimeter of the circuit. What's IA at 0 minus? Yep, so 9 volts divided by 2 ohms. Absolutely right. So let's rearrange this thing really quickly. So we could say that IL at 0 minus is going to be 9 volts plus 3IA, where IA is 9 volts over 2 ohms. And then we divide all of this by 7 ohms. My algebra work out okay there? Oh, the negative on this guy right here. Thank you for that. So +9 goes over, -3 goes over, divide by 7. Thank you. And let's throw this in. So 9 minus 3 times 9 over 2 divided by 7 gives me -9/14 of an amp, which is -0.643. Just gonna double check things here. Seems legit. Okay. So now we'll analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, we're gonna have our 9-volt source over here. Our switch is going to be open, so I'm just gonna open circuit right there. Here's my 2 ohm resistor through which a current IA at 0 plus flows. Seven ohm resistor right here. So my inductor current was defined, actually this should be my capacitor. So my capacitor was the voltage drop across my capacitor was 0 volts at 0 minus. It has to continue being 0 volts at 0 plus. So I'm going to replace my capacitor with a short circuit. Then over here, I'm going to have my inductor, which is pushing a current of -9/14 of an amp down. So here's V at 0 plus, IL at 0 plus, IC at 0 plus, and we know that V at 0 plus has to be V at 0 minus is 0 volts. IL at 0 plus has to be IL at 0 minus, so -9/14 of an amp. And IC at 0 plus, we're going to have to determine using circuit analysis. So we should be able to figure that out by inspection here. What is it? Yeah, so +9/14 of an amp. So effectively, we know that no current is going to be flowing around this path, because that's just going to look like a resistance to any current that flows. And so if it can flow through a short circuit or some resistive path, it's going to flow through the short circuit. Okay. So we would have, just for the sake of argument, negative 9/14 of an amp flowing up, which is the same as positive 9/14 of an amp flowing down. Okay. Do we need to analyze this circuit at t is equal to infinity at all? No. Because our dependent source, excuse me, our independent source is switched out of the circuit. So everything is going to be zero at infinity. Okay. Let me see if I even asked you guys. So I did ask you to do it at infinity, but the answer is just zero for everything, which you can determine by inspection. Okay. So the next thing that I want us to do is we're jumping ahead to, I guess this would be part D, where we're determining alpha and omega naught for this circuit. Okay. So let's start with omega naught, right? Omega naught, by definition, is the square root of 1 over LC. So that is the square root of 1 over, scroll up here, 25 millifarads. So 0.025 times 40 over 9. Comes out to be 3 radians per second. Okay. Our resistance will be a little bit more difficult. So let's draw our circuit during the transient condition. So that means my 9-volt source is open circuited. Here's my 2 ohm resistor. Here's my 3IA voltage source. Here's my current IA. Here's my 7 ohm resistor. And then here's my capacitor. And here's my inductor. So I just want to remind you guys explicitly that we're finding the equivalent resistance seen by our energy storage elements. So this is a Thevenin resistance, which means we need to be looking at a dead network. So we're going to turn off our voltage source, and then we're going to remove our energy storage elements. So this is the network that we're trying to find the equivalent resistance of. How do we find the equivalent resistance of a network that contains a dependent source? Test source method. Absolutely right, Henry. Thank you. So I'm going to put a test source here. What kind of test source should I put? Like realistically, it doesn't matter, but one of them is going to make things slightly easier than the other. So a current source here is going to make it easier because a current source lets us define what IA is, right? Yeah. So I'm going to put a 1 amp current source direction up, like so, and we are trying to find this voltage V test. Well, applying Kirchhoff's voltage law around this loop, what we find is that V test is equal to 7 ohms times 1 amp minus 3 IA, where IA is just 1 amp, plus 2 ohms times 1 amp So 7 minus 3 plus 2 is 6 volts. And from this, R equivalent is 6 ohms. Anybody got any beef with that? So from here, because this is a parallel RLC circuit, alpha is just 1 over twice R equivalent times C. So that's going to look like 1 over 2 times 6 ohms times 0.025 farads. So 1 over 2 times 6 times 0.025 looks like 3.33333 or 10 thirds. Let's see, Neppers per second. Since alpha is greater than omega naught, that means that this circuit is overdamped. We all okay with that assessment? All right. So now let's look at what we're trying to find. So we're trying to find an expression for IA of t valid for t greater than or equal to 0 plus. All right, so there are a couple of different ways that we can approach this, okay? So I'm just looking at my circuit diagram here. So one way that at least seems obvious to me, and it's actually not the method that I would choose, but it is the most glaringly obvious, would be to say that IA plus IC plus IL is equal to 0. Meaning that if we can find the inductor current, which we know we can, and we can find the the capacitor current, which we also know we can, we could find that current IA using Kirchhoff's current law. There is nothing remotely wrong with that, but that is not the laziest way to do this, which is why it is not the way that I am going to do it. Okay. What I am going to do, and this is less intuitive, but it will give us literally the exact same result. I know that the voltage drop across all three of these elements connected in series is just V of t, the capacitor voltage. I also know that those three elements connected in series look like a 6 ohm resistor because we found the equivalent resistance of it. So if I find V of t and divide that by 6 ohms, that is IA. Anybody got a beef with that line of reasoning? All right, so that's the approach that we're going to take. So from here, we know that V of t, treating this as if it were a capacitor voltage, because it absolutely is, will be of the form A1e to the S1t plus A2e to the S2t plus V at infinity. And we know for sure that this guy is 0, so we're just going to throw that bit away. Okay. So V at 0 plus is just going to look like A1 plus A2. V at 0 plus was 0, if memory serves me correctly. So our first equation on our system is A1 plus A2 is equal to 0. We okay thus far? Now, our capacitor current, IC of t, is C dV by dt. And so that's going to look like C times S1 A1 e to the S1t plus S2 A2 e to the s2t. IC at 0 plus reduces to C S1 A1 plus C S2 A2. Now, in order to get the coefficients for our variables A1 and A2, we're going to need to know what S1 is. S1 is negative alpha plus the square root of alpha squared minus omega naught squared. So that is negative 10/3 plus the square root of 10/3 squared minus 3 squared comes out to be negative 1.88036. So let's just call it 1.880 per second. I'm storing that in my calculator as A. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. So let me just go back and change the sign. That looks like negative 4.786. And I'm going to store this in my calculator as B. Okay. So putting these in, we have IC at 0 plus, which was 9/14 or something like that. Yep. Scroll too far. So we'll have negative 1.880 A1 minus 4.786 A2 is equal to 9/14 of an amp divided by 25 millifarads is going to be my second equation for my two equation, two unknown system. So all I did there is just move this common factor of C over to the other side so that I just have S1 A1 plus S2 A2 is equal to IC at 0 plus divided by C. Because that will let me put it in my calculator as lazily as I possibly can. Again, I want to do the least amount of work that I can do. So using my 2x2 system solver, my coefficient for A1 in my first equation is 1. My coefficient for A2 in my first equation is 1. My constant term is 0. My coefficient for A1 in my second equation is S1, which I have stored in my calculator as A. My coefficient for A2 in my second equation is negative 4.786 or S2, which I have stored in my calculator as B. And now I'm going to put 9/14 divided by 0.025 and solve. And I wind up getting A1 is 8.849 volts and A2 is negative 8.849 volts. So since IA is just V of T divided by 6 ohms, that's going to give us, so let me clear that, X over 6, 1.475 e to the negative 1.880 t minus 1.475 e to the negative 4.786 T amps. Now for the quote unquote hard part, which isn't all that hard. I just want to show you guys something here. We'll simulate this guy in LT Spice. So I'm going to effectively draw this circuit twice. One way would be kind of the official way, and then the other way would be the equally valid lazy way that you could use if you just could not for the life of you figure out how to make the dependent source work. So let's see, so voltage, that's tiny, so let's make that larger so I can kind of see the grid. So we don't actually need to include this 9-volt source in here at all since it's not really doing anything because it's disconnected. But because it's in my circuit diagram, I'm including it just for the hell of it. All right, so here I'm going to put what's called a behavioral voltage source. So BV, a behavioral voltage source is effectively an arbitrary dependent voltage source where we get to define how it works by including a mathematical function. So this would technically work as both a voltage controlled voltage source or a current controlled voltage source, which is why I'm using this one. It's just got the most adaptability. We could, if we were so inclined, so this is a current dependent voltage source, this H source, but it's a little bit more of a pain in the ass to use. So I don't use it unless I'm absolutely forced to. Okay. So behavioral voltage source, positive polarity on the left, negative polarity on the right. Resistor over here. Capacitor goes there. Oh, what the hell just happened? All right, so let's throw values and things here. So this is a 9-volt source. That's a 2-ohm resistor. That's a 7-ohm resistor. This was 25 milli. This is 4.444. Put my ground terminal on the negative polarity terminal of my capacitor. Label my capacitor voltage. Now I need to do this guy right here. So I'm making an assumption here, and I might have to fix this in a moment. IA is the current that's flowing through the resistor R1 down. So I'm just going to change this mathematical function. So I just right-clicked on that behavioral voltage source element, and I'm editing the value parameter to say that V is equal to 3 times the current flowing through resistor R1. And then once I run my simulation, I want to look at a current probe over that resistor R1 to make sure that it's in the same direction. If it isn't, I'll have to modify that either by rotating my resistor twice or just putting a damn negative sign in front of the IR1 just to make sure that it matches the actual direction of the current flowing through that thing. So that's my first circuit. My second circuit, I'm going to take a copy of this thing. Let's drop it over here. And I'm going to delete that, change this to a 6 ohm resistor, just the equivalent resistance. And then wire this thing up. And what should happen is I should get literally the exact same response. Which should make sense because the 6 ohm resistor is the equivalent resistance of that network. So, let's see. Oh, actually, let me change this to node VC1 and this guy over here to node VC2 so that we can do initial conditions for both sides. So the initial condition for voltage VC1 was 0 volts. The initial condition for current IL1 was 0 amps, if memory serves me correctly. The initial condition for voltage VC2 is 0 volts. And the initial condition for current IL2 is 0 amps. Dump all that in the middle. And let's run our transient analysis for, let's say 5 seconds. That might be too long. So my arrow is pointing down, so that's good. So that means I don't need to change signs on anything. Hold on, I feel like I messed up my initial conditions. I definitely did. The current should have been -9/14 of an amp. So let me go back and fix those. All right, so that's the current flowing through resistor R1, which is IA. Here's the current flowing through my equivalent resistance, and I'll be damned, they're literally the exact same thing because how could they not be? Tyler, you got a question about anything? Okay. And so now, just on top of all of this stuff, I'm going to add a trace that is my mathematical expression. So that would be 1.475 times exp of negative 1.880, I think. Yep. Times time minus 1.475 times exp negative 4.786, if memory serves me correctly. Yep. Times time. And then there should not be a DC component. And our analytical solution perfectly matched our simulation. Yes, David, how may I help you?
The initial conditions is just when the circuit at T goes near negative.
So I do that just because I'm too lazy to remember how to make a switch work. It's easier for me to just say it had this value than setting up a switch to actuate at the right time and all that kind of jazz. So yeah, so the initial conditions 100% correct are just what's going on in the capacitor and the inductor at 0 minus. Lee. Sure. So let me maximize this thing. So just for sake here, I used BV, which is a behavioral voltage source. If you ever have a behavioral current source or dependent current source, that's just BI. works the exact same way. So with the behavioral voltage source, I have my cursor over it. I right click and it brings up the component attribute editor. And I am just changing the value parameter and just saying V is equal to, so that's saying the voltage drop across this thing is equal to whatever mathematical expression I put in. And I put in 3 times the current flowing through resistor R1, because the current flowing through resistor R1 is the exact same as the current IA that we're looking for. Yep. So put it down here. Anyway, so here we go. Whole thing knocked out just a couple of minutes. So what do you guys want to talk about for the next 15 minutes? All right, well, I'll hang out in here in case you guys decide to ask something, but as far as I'm concerned, class is over. So on Monday, we are going to look at systems that are not parallel RLC circuits or series RLC circuits, right? So unfortunately, not everything is going to fall into one of those two very easy to figure out what's going on buckets. So we're going to look at general RLC circuits in the next class meeting. And then on Wednesday, we are going to effectively, it's the same thing, except that it's just, we might have 2 capacitors or 2 inductors where they can't be combined so that it still looks like a second order circuit because there are 2 energy storage elements. It's just not strictly RLC or, yeah, it's not strictly RLC. You can have 2 capacitors or 2 inductors. So, yeah. And then after that, I believe that means your test would be on next Friday. Everything's pushed back effectively class meeting because of that weather event thing. So, yeah. Yeah, sorry. And I can also make that larger so that you can see it. For what it's worth, it would not in any way, shape, or form bother me if you guys replaced the dependent sources with the equivalent resistance and all that kind of stuff, because it's literally the exact same thing. So if it gets to be just too much of a pain in the ass to figure out how to make those work for those couple of problems, it's no problem by me, by just treating it like a resistor, because it's all it's doing.